This is a walkthrough of the Chapter 14 review. Alright, so on number 1 here, our stated function is y equals 2 to the x minus 1. So that x minus 1, that's in our exponent. Alright, so the parent function of this is just y equals 2 to the x. Right, so that's the base function. And that here is graphed in purple. And the 2 points that we're most interested in here are 0, 1, which that's the point that every parent function of the exponential will go through. Every single one will go through the point 0, 1. Okay, the second point that we're most interested in is this point 1, 2. And that point comes from, because every exponential parent function goes through the point 1, and then whatever this base is, this number here, which in our case is 2. So that's where we get the point 1, 2. Okay, so we connect to those points, and we get this curve right here in purple. Okay, that's our parent function. But our function is 2 to the x minus 1. So that tells us that x minus 1, since it's in the exponent, that's a left or right movement. Left or right movements are always opposite of what we think they will be. So since this is minus 1, we would think that would move left 1, but it goes opposite of that and moves to the right 1. And that gives us this green function here. We took our point 0, 1, moved it right 1, and our point 1, 2, and moved it to the right 1. And that is our graph. Okay, the domain on an exponential function is always all real numbers. Okay, and the range, right, since where this graph curves down, this green line curves down, it approaches that x-axis, but it never touches the x-axis. Okay, we called that our asymptote. And the x-axis is actually the line y equals 0. So since it approaches the line y equals 0, but never touches it, that's where we get a range of y greater than 0. All right, on number 2, we have the exact same parent function. Okay, it's still y equals 2 to the x. This time, for our function, we are adding 2 outside of the exponent. Well, when we add or something outside of the exponent, that is an up or down movement. These go the way we think they would, so in this case, this one moves up 2. So we move our 2 points up 2, connect it with that same curve, and in green there is our graph. Domain, again, is always all real numbers. The range now, since we've moved it up 2, it no longer approaches that line y equals 0. Now it approaches the line moved up 2, which is now y equals 2. Since it approaches and then it goes and gets bigger than that, we say our range is y greater than 2. All right, for numbers 3 and 4, they also have the same parent function. It's graphed in purple on both of these. That parent function, the square root of x, goes through 3 key points. It goes through 0, 0, 1, 1, and 4, 2. We have those same points on both 3 and 4. Okay, on number 3, this negative 2 out in front says to take each of my y values, okay, and multiply them by negative 2. So in this case, this y value here at the origin is 0. When I multiply that by negative 2, it's still 0. That's why we're still at 0, 0. My second point has a y value of 1. I multiply that by negative 2, and that brings us down here to negative 2. My final point has a y value of 2. We multiply 2 by negative 2, and that brings us down here to negative 4. All right, for the domain and range, okay, for domain, we want to think, where is our x starting point? Well, our starting point on this graph is right here at the origin, which is the point 0, 0. So the x part of that is 0. Remember, our x's go left and right. Right, so this starts at 0 on the x and this graph goes to the right, well, to the right, our value's greater than 0. So that gives us a domain of x greater than or equal to 0. For the range, okay, again, we start at 0 on the y. Our y's go up and down. This graph points down, and although it kind of flattens out, it is still very slowly going down as well. Since this one goes down, that gives us our y less than or equal to 0. All right, on number 4, only thing we're doing is we are adding 4 under the square root, subtracting 2 outside. Well, the same within the exponent on the exponential, those went left or right. Underneath the square root also goes left and right. And again, they are opposite of what we think they would be. Since it's plus 4, okay, that actually moves us left 4. Minus 2, that moves us down 2. So I initially started at 0, 0, move our starting point left 4 and down 2, and we end up here. From there, we count our same points. So from our new start, we go right 1, up 1 for our second point, and right 4, up 2 for our third point. Connect those, and there's our new graph. Again, we use the starting point, in this case, -4 and -2, for our domain and range. Okay, domain is the x, so the -4 goes with that. Since the x's go left and right, and this graph points to the right, it's going to values greater than -4. So that gives us a domain of x greater than or equal to -4. Okay, on the y's, we start at -2, and this one points up. So again, it's going up very slowly. Okay, kind of almost flattens out, but it's still going up very, very slowly. So that's where we get a range of y greater than or equal to -2. All right, for number 5 here, this is an absolute value function. All right, so our absolute value parent function, okay, again, here is in purple, and that's just y equals the absolute value of x. Okay, so that starts at the origin. And from there, if we plug in values, well, if x is equal to 1, the absolute value of 1 is also 1. That's where we get the point 1, 1. If we plug in -1 for x, well, the absolute value of -1, again, is 1. That's where we get the point -1, 1. And so on. If I plug in 2 for x, I get 2 for y. If I plug in -2 for x, I also get 2 for y. So that's where I get the shape of this parent function. Now, for our function, 2 absolute value, x plus 2, and then plus 2 on the outside. Right? Again, since it's inside the absolute value, same as if it were under the square root, like in 4, or in the exponent, like 1, those are our left and right movements. Those are opposite of what we would think. So in this case, plus 2 actually moves us left 2. Plus 2 on the outside is our up and down movement, and those are the direction we would expect. So plus 2 moves us up 2. So we take our starting point, left 2 and up 2. That gives us our new starting point. All right, the 2 out in front, the same as the 2 out in front on number 3, well, -2 in that case. We multiplied all the y values by -2. Well, now we're just going to multiply all of the y values by +2. So instead of going right 1, up 1, that y value here was 1. I'm going to multiply that by 2. So now we go right 1, up 2. We went right 2, up 2 in the parent function. So now we multiply that y by 2. So we go right 2, up 4. And then the opposite on the other side. These absolute value functions are always going to be symmetrical. So that's where we end up with our final function in green. All right, for number 6, our piecewise function here, we want to graph each part individually. All right, so this, our domain restrictions here, tell us where our break line is going to be. And that's at x equals 3. So that's the little dashed line we have here on x equals 3. All right, if we look at the purple part here, we want to graph that. Well, this is in slope-intercept form, y equals mx plus b. So we have a slope of 2 and a y-intercept of -1. We started our y-intercept of -1, and then we just count our slope from there. Well, slope of 2 says go up 2, right 1, up 2, right 1, up 2, right 1. Now we're at our break line. Well, since this piece, the absolute, or the inequality there, does not have the equal to part, okay, that gives us an open dot on our break line with that one. We connect our dots, and that's that piece of the function. All right, our second piece of the function is when x is greater than or equal to 3. Well, this break line here, I'm greater than 3 when I'm to the right of this break line in this region over here. So now again, we want to graph this line. Well, this has a y-intercept of 5 and a slope of 1/3. So we go up to 5, 5, and then from there, we count our slope of 1/3. Up 1, right 3, that gets us to our break line. This is a solid dot because our inequality has the equal to part. If we go 1 point past that, up 1, right 3, that's our second point. Now, even though we used the y-intercept to help us find where this equation was, we don't graph the y-intercept because it is to the left of our break line. In this piece, the 1/3 x plus 5 piece, only exists to the right of our break line. So we only use those 2 points. All right, moving on to number 7. All right, so on number 7, we're given the graph, and we need to write the piecewise definition. All right, so the best place to start is to write the equations of the 3 different pieces. Okay, so we'll start with this piece to the left over here that's kind of highlighted in purple. So I want the equation of this line. Well, for the equation of a line, I need a slope and I need a y-intercept. To find the slope, okay, we look at one point where it goes through, in this case right here, it goes through that point, and then we want to find another point. Okay, so if we have this point where it goes through and this point, okay, slope is rise over run, so we count up 1, right 2, so that gives us a slope of 1/2. If we continued that slope, up 1, right 2, okay, and there's to our next point, up 1, right 2, that gives us that y-intercept on that piece right there. So that's why we get the equation 1/2 x plus 2. All right, now if we look at the green piece here, well, the slope on that piece, my rise over run, well, I don't go up any, but I go right 1. Well, 0 over 1 is still 0, so we have a slope of 0. That's why we don't have any of that 0x or any x portion out in front. But the y-intercept on this is 3, crosses the y-axis right here at 3. That's why we get an equation of just 3 for that piece. Our last piece, up here in pink, right? Again, if we look at this slope, well, if we start here, we go up 1, right 1, okay? That gets us to our next point, so that gets us our slope of 1. And if we trace this back, okay, down 1, left 1, down, left, we hit the y-axis right there at the point 1. So that gives us our y-intercept of positive 1. So now we have our three pieces, 1/2 x plus 2, 3, and x plus 1. Now we need the domain restrictions for each piece. Well, we write these vertical lines here where it's clear that it changes from one piece to the other. All right? In this first break on the left, okay, well, that's the vertical line at x equals -2. Now this purple piece we see only exists left of that blue line. Well, left of the blue line are values less than -2. So that's why we get x less than -2. And since this has an open dot on this piece, we don't get the equal to part on that inequality. For the green piece, okay, it lies between the two break lines. So that's where we have to write our compound inequality. With a compound inequality, we have the variable in the middle, and then the bound to the left, in this case -2 on the left side, the bound to the right, in this case +3 on the right side. We see this little green piece is when x is greater than -2, okay, that's going to the right, greater than -2, but also less than +3. Since these have our solid dots here and here, this gives us the equal to part. So this compound inequality represents x greater than or equal to -2 and x less than or equal to 3. Then our last part, okay, starts on our break line and goes to the right. So if this break line is at x equals 3, this is pointing to values going to the right, to values greater than 3 on the x. And no equal to on that part because it is an open dot. All right, for numbers 8 and 9, those just require putting them into your graphing calculator and seeing where they would cross. So we would take each part, in this case square root of 2x, and 2 times the square root of x plus 3. We would put them each on their own lines in the y equals 2 part of your graphing calculator. And then when you graph them, you'd see if they cross or if they don't. In the case of number 8, it's clear from the picture that they do not cross. If two graphs don't cross, then they have no solution. For number 9, we can put -5 on one of those lines in the y equals 2, and we can put negative square root of x on one of those lines. All right, when we hit graph on those, okay, it's clear that they cross, but we're not real sure where. Now we can either use our calc and the intersect function to find where they cross, or you can use the table function, find where the y values are the same, and that will give you your answer as well. So you can use either of those two methods. All right, for number 10, we're asked to rewrite this function so that it'll be easier to graph. All right, well, anytime we're asked to rewrite, we're always going to be factoring out whatever this number is in front of the x. Okay, and that number is also always going to be a perfect square. It's going to be a 4 or a 9 or a 16, 25, 36, one of those numbers. In this case, it's 16. Well, we see 48 is also a multiple of 16. So 16 is a factor of 48. If we factor 16 out of both of those, 16 times x plus 3. We factor the 16 out of both the 16x and the 48. Now, we can take the square root of the 16, so it comes out of the square root as 4. X plus 3 we cannot take the square root of, so it stays under the square root as our x plus 3. And our minus 3 just carries on down. So now we have it in this form we can describe what happens. The 4 in front is a stretch. Any number greater than 1 in front is going to be a stretch. Only fractions are a compression. X plus 3 under the square root is opposite of what we think. We think right 3 since it's positive. Opposite of that is left 3. Negative 3 on the outside, that's our up and down. It's minus 3, so that shifts down 3. All right, on number 11 here, we are just looking at this graph. Okay, this is our f of x graph right here. On the right, it wants us to graph if we take that and add 4 inside the parenthesis. Well, again, anytime it's inside the parenthesis or under the square root, or as we saw in the first example, in the exponent, those are our left and right. And those are opposite of what we think. In this case, adding 4 inside, opposite of what we think. So this just shifts the entire graph left 4. So we just take all of our points from each part and shift them each left 4 units. All right, for our last page here, all right, for these first two, 12 and 13, we're using our continuously compounded interest formula. So our A equals P times E to the RT. So RT, that entire part is in the exponent. So then it's just a matter of identifying which pieces of that we have. Well, if we start with 400, that's our principal. P stands for principal, how much we start with. R is our rate, okay, that is the interest rate. And when we put it in the formula, we always have to put it in as a decimal. T is our time, so how long has it been in the account, how many years. And then it's just a matter of plugging these values into your graphing calculator to get your solution. In this case, we put in 400 times E to the 0.035 times 10, all of that in the exponent, and we get $576.63. On 13, we are given how much you put in the account, your initial amount, your principal, that's $2,000. We're given the interest, and then we're given how much you want to end with. So we're given our A in this case. What we need to find is how long it will take to get there. So we want to know when the investment will be more than $5,000. So here it's just a matter of plugging in years and finding out when you get greater than that $5,000. In this case, plugging in, I tried 13, 14, 15, and got up to 16 before I saw that that was how many years it was going to take just to get over that limit. So 15 years was just under $5,000. 16 years was that first year when it was over $5,000. All right, for number 14, all right, this is our combining functions. All right, we're given the two functions, 4x squared minus 4 and x plus 1. All right, subtracting the functions, 4 or f minus g of x means subtract one function from the other. In this case, f of x, 4x squared minus 4, minus g of x, which is x plus 1. The key here is making sure that you distribute the negative sign to both terms, to both the x and the negative 1. Okay, when we do, this becomes 4x squared minus 4 minus x minus 1. All right, well, the only like terms we have here are the negative 4 and the negative 1. We put those together for negative 5. But the 4x squared and the negative x just stay the way that they are. All right, when we are multiplying f times g of x, okay, that is f of x times g of x. Well, when I have a binomial times a binomial, we need to remember to use the distributive property. So we have to multiply each term in the front by each term in the second. When we do that, we get the 4 terms, 4x cubed plus 4x squared minus 4x minus 4. And again, none of those are like terms, so we can't put anything together. For 16, f divided by g of x, right, that's where we're simply writing one function over top of the other. In this case, we're writing 4x squared minus 4 over top of x plus 1. Now, that would be sufficient for what we have been doing, okay, and that's what I told you from the beginning, just writing one function over the other. But this one does have the ability to be simplified also. So we can factor a 4 out of the top function. And then x squared minus 1, well, that actually factors into x plus 1 and x minus 1. From there, we have the terms x plus 1 on both the top and the bottom. Since that's a factor on both the top and the bottom, those can be canceled, and we're left with just 4 times x minus 1. All right, on number 17, we are given merchandise sales function and ticket sales function. What is the band's total earnings? Well, their earnings come from merchandise sales and ticket sales, so it's the combination of m of x and t of x. If we add those together, 1.1x plus 5x minus 200, well, 1.1x and 5x are like terms. 5 plus 1.1 is 6.1x minus 200. How much can the band expect to earn if 300 people attend the concert? Well, now 300 is your number of people. So we substitute 300 in for x into this equation. When we do that, plug it into our calculator to get our values, we end up with a total of $1,630. And there is our walkthrough of your unit review.